We have graded homework 1. So after class, you can come and pick it up. Not before class, because otherwise assume that I would just give the lecture and you would just read your homework solutions. So that wouldn't be effective. But when we finish, then you can just get it. And if you have questions, you don't agree with your grades, then you can just talk to the TAs during their office hours. The plan for today is to discuss Gaussian processes, especially Gaussian processes for regression. So it will be a new algorithm for regression. And we will follow the treatment of this book. So if you go to this website, then actually you can download the PDF of this book. And we will just discuss, I think, chapter 1 or chapter 2. Today there will be lots of derivations. And I'm just wondering if you printed out the slides. Because if you print out the slides, then it would be just easier for you to make some notes. But I will try to be slow. And it's my request to make me slow, so ask questions whenever you get lost. Some of the formulas will be quite complicated, so it's a warning, and you have to pay attention. The main ideas are very simple, but the calculations, the details of the calculations will be complicated. And there will be some calculations where it will be just your homework to verify those calculations. Otherwise, it would take like 3 lectures to finish all the details. Okay, so the plan is that we discuss what kind of regression problems we exactly want to solve today. And it turns out that to handle these kind of regression problems, we will need to know some properties of multivariate Gaussian distributions. So we will discuss some properties of multivariate Gaussian distributions. And we will also need some properties of ridge regression. So we will discuss ridge regression as well. And then we will start discussing Gaussian processes for regression. And there will be 2 different ways to introduce Gaussian processes for regression. One of them is called so-called weight space view, which is nothing else, just the Bayesian ridge regression plus kernel trick. So it's a kernelized Bayesian ridge regression. That's what we are going to discuss. And in the slides and in the book, you can see another introduction to Gaussian, other ways of introducing Gaussian processes, which is the so-called function space view. We are not going to discuss this, but the slides are there, and if you look at the slides and you have questions, then we can chat more about that. So today we are going to discuss Bayesian ridge regression with kernel trick, and oh, sure. And then this will lead to Gaussian processes. Can you see it well? I don't know how strong the projector is. Okay. So what kind of regression methods we know so far? We know linear regression, I assume. Logistic regression. We just learned support vector regression. Do we know KNN regression, k-nearest neighbor-based regression? Who knows k-nearest neighbor regression? 5%. So that's another very simple way of doing regression. So for example, I'm in a 2D space. These are input points. And in each input point, I have an output value. I want to do a 2D regression. So I don't know, the output value in this point is 5, 0, 1, 2, 3. And I want to do a 2D regression, such as I want to, if you select a point, I want a query point, I want to predict an estimated value of the 2D regression function here. And what you do is that you fix a k, so let k be, I don't know, 3. You calculate the 3 nearest neighbors to this query point, and you average the output values. So the estimated value of this would be 0 plus 3 plus 1 divided by 3.
Why is this called regression?
So what's regression? Regression is that you have input-output pairs, and in a new query point, you want to predict the output. Right? So what would be a 2D regression problem? You have two-dimensional input points and say one-dimensional output. That's your training set. And then someone provides a query point like this, and you want to predict the value there. Does it make sense? Right, so in regression, generally you have some input points, some output values. That's your training set. And if someone provides a new query point, you want to predict the output value here. In this one-dimensional case, you can do the same thing. That's, for example, you fix k3. For this query point, you calculate the 3 nearest neighbors, and you calculate the empirical average of those points. Okay? So all these regression methods that we know, they give us a point estimate. In that sense that, like in this case, these are the input-output pairs. You have a query point, and the algorithm would say that I think in this query point, the function value is this expression. Or here, I would say in this point, the function value is 0 plus 3 plus 1 divided by 3. What we want to do is we want to design a regression methods that would give you a confidence as well, where the algorithm would say that I think with this probability the output value is this. With this probability the output value is this. So instead of just predicting a value, we want to predict a distribution. Okay, because that would be more meaningful quite often, right? That instead of just saying the output value is 0.2, I would predict a distribution for the output values. But these algorithms that we learned so far, they cannot do this. Okay, so ideally we would like something like this, that you have input-output pairs. So this is a one-dimensional regression, input-output pairs. And in any query point, I would like to also predict a confidence interval for the points where I would say that with 95% probability, I think the values are between this region.
But don't you have the confidence interval theory for linear regression?
So what would be that?
So you assume that the errors are normally independent normally distributed random variables in the least square estimate, least square regression, right? You don't do that?
So what's your model again?
It's the linear regression, right?
Sure.
So y equals, what is it, the constant plus x times beta plus an error term epsilon, right? So you assume that epsilons are independent.
So how?
And then you can.
But how x and y generated? So just because you have a noise model for the probability model for your noise,
Yes.
it doesn't mean you will have a probability model in every query point x. Right? So in a query point x, I want to predict a distribution for the output values.
Okay.
You have a noise model for
Right.
Gaussian noise model.
On the feature space?
Yeah, so we need a model for all x, y's to answer this question.
Okay.
Good point. Okay, does it make sense what we want? So in each query point x, we want to predict a confidence interval as well.
Just a confidence interval, but will that tell you exactly if I give you a point? If I give you a pair of input and possible output, will you give me what's the probability that it's correct?
Mm-hmm. Right, so if you give me a query point here, then I would say that my prediction would be a Gaussian distribution with some mean value and with some covariance. All right, so this is motivation 1. Motivation 2 is that with Alex, we learned that we can kernelize so many different things, right? And just for fun, let's kernelize linear ridge regression and see what we get. Right, these two things will be the same, but spoiler alert. All right, but for now we can just stick to this, that this is our goal. Okay, so we will try to answer these 3 different questions. That you have some input-output pairs, and the algorithm will say that, the algorithm would say that I think this is that where the most probable regression function is, say this function. So that's one thing. So I want to predict the most probable regression function. The other thing you want to do, that you want to be able to sample from the possible regression functions, right? So the algorithm wouldn't just say that, hey, this is for sure the true regression function. It would give a probability distribution of the possible regression functions, and you would like to be able to sample from those sets, like this red, green, blue regression functions. They all look like possible regression functions with different probabilities, but you would like to be able to sample from these sets.
Does this assume there is no noise at observations?
Oh, here, right. So in this case, I assume that there's no noise in the observations, but we could generalize this to the case where you assume that there's noise in the observations as well. Good point. Okay, then what you would see that there would be some error bounds here too.
Are you sampling possible points or possible functions?
I will sample possible regression functions. Okay, but you can also ask that here is a query point x prime. Please tell me the possible values with confidence in x prime. Are these goals clear? Who lost me already? Okay, so it seems everyone is following so far. Okay, so these are our goals. So we want to derive a regression methods that can provide some confidence intervals for us. And in particular, what we will do is that in each query point, the algorithm will predict the Gaussian distribution with some mean value and variance, and that will be the output of the algorithm. So to be able to do this regression that we want, we need to know some properties of the multivariate Gaussian distributions. So let's discuss Gaussian distributions for a few minutes. So I hope everyone knows this is the one-dimensional Gaussian distribution, the density function of one-dimensional Gaussian distribution. It has 2 parameters, mean and variance. And this could be generalized to d-dimensional vector spaces. So this is a density function of a d-dimensional Gaussian distribution. In this case, the Gaussian distribution is 2-dimensional. It has a mean vector parameter and the covariance matrix sigma. And this is the density function, where this absolute value denotes the determinant. Everyone knows that, right? Okay, so this, in this case, this is just a 2-dimensional Gaussian distribution. And the covariance matrix is always symmetric and positive semi-definite. That is, for every x vector, x transpose sigma x is non-negative. Okay, so this is just a case of a 2-dimensional Gaussian distribution with mean vector 0 and covariance matrix 1, 0.8, 0.81. So what it shows is that there's a high correlation between the two dimensions, say x and y. And that's why you can see that this distribution is aligned like this. Sometimes we always illustrate two-dimensional Gaussian densities with these level sets. So with the same Gaussian distribution, these would be the level sets. And you can see that there's high correlation between the two dimensions. The correlation is 0.8. All right, there is a very important property that we need to know, that if you have a multivariate Gaussian distribution, then the marginal distributions of that Gaussian distribution, they are also Gaussians. So for example, if I have a multivariate Gaussian distribution and I partition the dimension to xa and xb, so these are random variables, these are random variables, then they would have, they are xa and xb, they are also Gaussian distributions. They have mean values mu a and mu b. The original mean vector was mu. And I can partition the covariance matrix sigma, the original covariance matrix, to this way, that's sigma a, sigma ab, and so on, sigma bb. And the marginal distribution of xa random variable will be just a Gaussian distribution with mean vector mu a and covariance matrix sigma a. Okay, that's trivial so far. So if we have a two-dimensional Gaussian distribution, then the marginals just means if you project, so these are sample points from a Gaussian distribution. If you project all these points to one dimension, then the projected points would be Gaussians. Similarly, if you project all these points to the other dimension, they would be Gaussians as well with these parameters. All right, so that was easy. So marginalization is just means you project the points. The other interesting property of Gaussian distributions is that the conditional distributions are Gaussians as well. So it means that instead of projecting all the points to one dimension, if I fix, say, a point here, and I just get this slice, that slice would have Gaussian distribution as well. Okay? And this is where the calculation gets tricky. So if the original Gaussian distribution had covariance matrix sigma, sigma a, sigma ab, sigma b, sigma bb. So I split the original random variables to xa and xb. Then the probability distribution of xa given xb will be a Gaussian distribution. And now the calculations got a bit messy because this conditional Gaussian distribution will have a mean parameter denoted with mu ab and the covariance matrix denoted with lambda a inverse, where the formulations for mu ab is given by this formula and for lambda it's given by this formula, where lambda is just the inverse of the covariance matrix. So I'm curious now, who doesn't know this? Who doesn't know the properties of conditional Gaussian distributions? They should raise hands. Okay, so let's slow down then. So we will use these a lot today. So I have a covariance matrix sigma, which is sigma AA, sigma AB, sigma BA, sigma BB. Okay, this is a covariance matrix of a Gaussian variable, random variable x, which is just, say, xa and xb together. And I want to calculate the conditional distribution of xa given xb. I claim that this xa given xb, that's a Gaussian distribution. It will have a mean parameter mu a that's denoted with mu a given b, and it will have a covariance matrix that's In this case, it's denoted with lambda A inverse. And let lambda matrix be the inverse of sigma. So sigma is a covariance matrix. I calculate its inverse. I get another matrix. And I partition the same way lambda as I partition sigma. So this way there will be a lambda AA block here, lambda AB block here, lambda BA block here, lambda BB block here. Yes?
Why is mu A given B dependent on XB? So you have lambda AA inverse lambda AB XB minus.
Right. So what do? We calculate the conditional distribution of XA given XB. We are here. We calculate, so say, right, let this guy be XB. This is, say, XA in the previous example. And I want to calculate the conditional distribution of this Gaussian distribution given XB. So what's the conditional distribution of XA given XB? That will be the distribution of this. So that distribution has to depend on XB, right? Okay? So if I calculate the conditional distribution of XA given XB, that conditional distribution has to depend on XB. And it just turns out this is how it depends on XB, that the mean will be shifted to this value from mu A, that will be the new mean value. Yes?
What does it mean to have a normal of XA given mu AB?
So you have a joint Gaussian distribution, XA and XB. XA and XB, they are two random variables, jointly they are Gaussian. That's clear so far, right? And so XA and XB, they are two random variables, jointly they are Gaussian. I want to calculate the conditional distribution of XA, random variable, given XB.
No, my question is, when we are specifying the mean of the normal, we write XA given mu AB.
Oh, so what it means, that's your question?
Yeah.
So okay, so this is a density function of a Gaussian at a place XA with mean parameter this and covariance this. All right, so it's like this. Okay, so it turns out that the mean of this conditional Gaussian distribution mu AB is just the original mean of A, and then we modify this mean to be this, that's its lambda AA inverse times lambda AB. Again, lambda is just the inverse of the covariance matrix times XB minus mu A.
How did you get to that?
So the calculation of this would be like, I don't know, 10 minutes of calculation. So you have to believe me here. Or it's better if you check yourself. But the proofs are really in every statistics book, Wikipedia, so you can find it. Yep.
Is XB minus mu B or mu A?
It's XB minus mu A, I believe.
Where does mu B come in?
I think it should be mu B.
You might be right, so let me think. So
Should be mu B.
Wherever XB occurs, it must be centered with respect to mu B, right? So make sense that way.
So actually, a simple way to check is if I partition a joint Gaussian into two components,
Yep.
that each component have different dimensions, then XB and mu A are in different.
Oh, you are right. Yep. Right. Yeah, that's a good point. So that might be mu B, and then I believe this is mu B too.
AB.
Oops. Okay. All right, and this lambda AA, the inverse of this guy, it turns out that this is the so-called Schur complement of this covariance matrix sigma, so this Schur complement of this matrix sigma BB in this covariance matrix sigma. Who doesn't know what Schur complement is? Okay, so let's go back there. So there's a theorem which is very important. So if you have a matrix and you partition this matrix to blocks and say this matrix is invertible, the original matrix, then it turns out that you can calculate the inverse of this matrix with these formulas. Okay, so the inverse of this matrix would be just this matrix, this here. So in other words, you can double check. If you multiply this matrix with this matrix, you should get the identity matrix. And we say that the Schur complement of this block A is defined with this expression, D minus C times A inverse B. And the Schur complement of the analog way, it's A minus this guy times the inverse of D times C. Okay, so these are the definitions. And why they are important? Because they simplify your notation a little bit. So the inverse of this matrix, it will be just, in this part, it will be the inverse of the Schur complement, D. And here, in this part, it will be the inverse of the Schur complement A. And again, these parts, it will be just, you see that D inverse times C times the inverse of the Schur complement D. Okay, so these are just some algebra identities that you can check yourself that they hold. Okay? So maybe I write this here. So we have a matrix A, B, C, D. Then the Schur complement of this matrix, this block at A, is just D minus C times A inverse B. All right, so what's important for us here is that the new covariance matrix of this conditional distribution is just the Schur complement of this guy in the original covariance matrix. Yes?
Sigma BA is sigma AB, right?
Sigma AB is sigma BE transposed.
Yeah.
Okay? So the sigma is symmetric matrix. Sigma A is symmetric, sigma BB is symmetric. All right, so everyone is friends now with Schur complement and conditional distributions of Gaussians. All right, so far we were able to visualize one-dimensional and two-dimensional Gaussian distributions. If I want to visualize higher dimensional distributions, then I'm in a trouble. So I don't know how to do that. But one thing I can do that, for example, if I want to visualize an 8-dimensional Gaussian distribution, then at least I can do this, that here are dimension 1, dimension 2, dimension 3, dimension 8, and I can show the mean of those the marginal Gaussians and the variance of those marginal Gaussians. What I cannot show to you this way is what's the covariance between these marginal distributions, right? Okay, so if I have a 8-dimensional Gaussian distributions, then say these are the marginal distributions. The notation is that the mean of dimension 6 is denoted with mu6, and the variance of this marginal Gaussian distribution is denoted with sigma squared 6. All right. So in this case, I indexed this Gaussian distribution with 8 integers, right? So each integer was a Gaussian distribution. And then you might ask the question, why stop here? Why don't we just index with all the integer numbers?
I mean, we have a certain dimension.
Yeah, so I want to generalize the Gaussian concept from fixed finite dimensions to other dimensions, or
so you want to visualize it.
So I want to visualize, and I cannot do that in 8 dimension. And now I want to generalize Gaussian distributions from fixed 8 or finite dimensions to larger index domains. Does it make sense? So, for example, I'm wondering if there would be a way to generalize Gaussian distributions from fixed finite dimensions to all integers as index set. Yes, you had the question.
Yes, how would you represent the covariance matrix?
So we will come to that, but so the first question we are wondering now, that we know what that means, that we have an 8-dimensional Gaussian distribution. I cannot really visualize it, but I can at least visualize the mean and the variance of each marginal. Now we are wondering if I can generalize this concept of finite dimensional Gaussians to something else, for example, infinite dimensional Gaussians, such a way that each dimension in that infinite dimensional Gaussians would be indexed, say, with the integer numbers. Okay, so for integer 9, there would be another Gaussian distribution. Integer 10, there would be another Gaussian distribution. And for any integer numbers, there would be a Gaussian distribution. And somehow these Gaussian distributions wouldn't be independent from each other, but they would be correlated in some way. Okay? And if we did that, so say we can solve this problem, that for all integer I would get to a Gaussian distribution, then you can ask even more general questions. Can I generalize the index set to be all real numbers? That for each real number as an index, there would be a Gaussian distribution with some mean and with some covariance. And this Gaussian distribution somehow would be correlated with the other Gaussian distributions. All right, so it turns out if we do that, so if there's a way to do that, then the mean of these Gaussian distributions in each dimension, so for example, if the index set is all the real numbers, then the mean of these Gaussian distributions in each, that would be just a function, where the domain of that function is the index set. Okay, so in this case, just imagine that in each real number index, there's defined a Gaussian distribution, one-dimensional Gaussian distribution, with some mean vector and some variance.
Where's the variance here?
So for each marginal would have a variance. I didn't talk about covariances yet.
So it's two-dimensional function here?
This is a one-dimensional function. This is the domain of the function. These are the outputs.
But where's the variance?
Variance of what?
It's a function from R to R2.
Right, so it's a R to R function. So your question is variance of what?
The Gaussian. So you have here.
But which Gaussian?
Like, you have a dot, and then you need to give me also the mean and also the variance.
So the mean, so the index set will be all the real numbers. For index x, the mean of the Gaussian will be, say, mu x. The variance of that Gaussian will be sigma squared x. So for in each location x, I can define a Gaussian distribution. Okay?
So you draw a continuous function there. What makes us to think that it should be continuous? Or do we make any regularity conditions on this?
Right, so if I just do that for in each x, there would be a Gaussian distribution. It wouldn't be continuous. But what we will do, that with we want that Gaussian distributions, indexes that are closer to each other, I want their correlation to be higher. So if there's two index close to each other, I want their mean to be close to each other and their variance to be close to each other. And this way you can define smooth functions as well. So what we are going to do, that we will, for each index x and y, I also want to define their correlation or covariance. And we will define a correlation or covariance function k x y. Yep.
You don't want like correlations between more?
So it will be covariance between, for any x and y, I want to define.
For example, x1, x2, x3, xn, the correlation between.
Okay, so we will come to that point 1 second. Yes.
Another question that, following what you said, then you're going to require that the limit of when x and the distance between x and y goes to infinity, then k is going to 0 as well. So because they're, or not really.
That doesn't matter to me. I just want when the indexes are close to each other, then the means are close and the correlation between them, that's increasing.
Does this have any relation to the random walk? So where you have the increments, you have.
So you can think of.
So the increments are Gaussian distribution.
That. Sure. So yes.
When you move from the discrete case to the continuous case, there's like a kind of intuitions. Like in the discrete case, we know it is dimensions. So in the real line setting, we can do this. Of course, we can do the same thing here, but it's just what does it mean of having a dimension?
So the dimension will be infinity in this case. So when you add more and more dimensions, right, it's increasing. And when the index set is the integer numbers, we have countable many dimensions. When the index set is the real numbers, we have uncountable many dimensions for that Gaussian distribution.
So that means you have a movement from Z to R, and then you actually, because I'm still thinking in terms of infinite dimensions, it is still Z, not R yet.
No, it is R.
So I'm changed, right? So index set can be either Z, or it could be more general. The index set could be R. When the index set is Z, then the dimensions are infinite, but countable many infinite, right? When the index set is R, this is infinite, but uncountably infinite, the number of dimensions. So now we are talking about Gaussian distributions whose dimensions are, so in case of R, when the index set is R, the dimension is uncountably infinite. And what we need for this is we need to define a mu function that for each x, that would be the mean of the Gaussians. I also want to define the correlation between any two Gaussian distributions. So if between the covariance between Gaussians at index x and index y will be defined with this kxy function. And now back to your point. So this is, we are not going to prove it. But it turns out that just defining these two functions, it's enough to define Gaussian distribution, or a so-called Gaussian process, which has this property that if you fix any finite number of dimensions, jointly they will be Gaussians. Okay, so that answers your question, that if I have this index set R, it turns out that if I define mu x and I define in a correct way these kxy functions, they can define so-called Gaussian process, which has this property that for each index x, it's a Gaussian distribution, and if you choose any finite number of index points, jointly that will be a finite dimensional Gaussian distribution.
That's Kolmogorov, Tuche, something like that. Some extension.
So it's it's the extension of that Kolmogorov theorem.
Are there any constraints on K for that?
Good point. So let's see. So what kind of constraints we want on K?
They want to be you need to be at this consistent.
Right. So let's see what kind of properties we want from this K function. So on mu, probably we don't have any constraints, right? The mean can be anything. Finite. It should be finite, right? But what constraints do we have on K?
If you marginalize
right. So
Should be sort of infinite rank.
infinite rank.
If we fix more than, let's say, rank of K is.
So K is a function.
Yeah. So
But
if
then when
you
you fix endpoints,
Mm-hmm.
the rank of the matrix that you get is less than n. You get determinant 0 and the denominator the Gaussian.
But so why is it a problem? So you might be right. I just want to understand why it would be a problem. So so for example, it might happen that the variance is just 0, so the function became constant, right? But I've heard something about positive semi-definites.
Points and the matrix generated.
Right. So for example, what is kxx? That's the variance of the Gaussian when I fix the index to be x. So this kxx has to be non-negative for sure, right? Because that's the variance of that.
it needs to be sigma squared. Right? It needs to be
It's sigma squared, exactly. Sigma x squared. It has to be symmetric as well, because kxy should be the same as kyx.
And if you can get the joint distribution of x and y just by looking at kx, right? And then you also want to know that if you take the joint and you marginalize x, then you get again kx. Is that trivial?
So once again,
So if you can build sigma xy as kxx, kyy.
so sigma x.
So
Sure, but so let's forget sigma for now. So I just fixed mu x and I fixed kxy. So the question is what kind of property. So from kxy I can define sigma squared x because.
and from kxy you can define.
So from the function k, I can define sigma to be this guy, right? But because it's covariance, it has to be non-negative. Symmetric, right? So k has to be symmetric.
it should be an inner product.
Yes.
Generate a norm in itself, right? So that we get always this positive function.
Right, so we are going to the right direction. So another property we heard, if I fix any finite number of indexes, so for example, x1, x2, I don't know, x3, then I can calculate, k is defined, so I can calculate a so-called gram matrix where the elements are k, x1, x1, oops, and so on, and in the I and j place, it's k, xi, xj. Let's call this gram matrix. Then, because we discussed that for any fixed finite indexes, x1, x2, x3, it has to be jointly Gaussian. It means that this has to be a covariance matrix, which means it has to be symmetric and positive semi-definite. Okay, so K has to have this property that if you fix any finite indexes and you calculate this gram matrix from those finite indexes, then K has to be positive semi-definite. Okay, and that's one definition of, so for saying that K is a positive semi-definite function. And if you remember Alex, he had another definition of being positive semi-definite function. Do you remember that?
Versus theorem?
Yeah, so how was that?
So for any function the f over any x and y in say some dimension, and the two-dimensional integral is always greater than or equal to 0.
Right, so for any function f,
fx,
fy,
yeah, the dx dy.
this has to be non-negative, right? If I integrate this with respect to x and y. Okay, so it turns out that these two definitions are equivalent actually. That K, so K is symmetric, and for any function f, this integral is non-negative. It turns out it's the same as what we just said, that for any fixed finite number of indexes, this gram matrix has to be positive semi-definite. Okay, and just one more note on this, that if you think this is, if the gram matrix is say capital K, and then it's very similar to this that say F transpose KF is non-negative for K gram matrices, right? So this kind of the same thing. All right, so this is where we are now. So what we discussed is that given if you define a mean function mu x, and this K function between indexes x and z, that you can prove that it's enough to define a Gaussian process which has these properties that we just discussed, that for any fixed finite indexes, the joint distribution of those random variables, they would be Gaussians. And you could even be more ridiculous, that the index set, instead of being R, it could be finite dimensional vectors. So for index, in this case, the index set is R2. And then you can define surfaces this way.
What is an example in which you use RD? Or because RD and R have the same size. Is there any case in which you use R to the R?
Yes, so right. So when we use index set R, we will use that in problems where I want to learn a regression from R to say R. When I want to learn a regression from say R2 to R, then the index set would be R2. Okay, so what we have now, we discussed infinite dimensional Gaussian distributions. Let's just call them processes. Okay, so we discussed Gaussian processes which have this property that, like just from Gaussian distribution, you can sample from Gaussian processes as well. And in this case, if you sample from a Gaussian process, the sample would be a function. Right? So for each marginal, you would have a Gaussian row with some mean and with some variance. And these Gaussians will be all correlated. But because the index set in this case is R, if you sample from this Gaussian process, then in effect what you do, that you sample from a space of distributions. Okay, if the index set is R2, then you sample from the space of surfaces. And what we want to do is that in machine learning, that we will have a training set of input-output pairs. And we want to learn a Gaussian process that's somehow compatible with the training set. So that when you sample, that for example, in this case, if these are the input-output pairs, I want to learn that mean function and say covariance function, that when I sample either the blue or the green or the red curve, the red functions, somehow they look compatible with my training set in that sense that you can see that here the variance is smaller, here the variance is higher, and so on.
These samples need not be continuous at all, right?
The sample points, no, they are just fine. You have finite sample points like x1, y1, x2, y2, x and yn. That's what you have in your training set.
Not the training samples, what we sample from a Gaussian process, the function that we sample.
So, right. So, your question is why it's a continuous function, right?
Yeah, it need not be.
It may not be. So, it depends on how you define your kernel function. How you define the covariance between points indexes x and y, right? And it also depends on your mean function mu as well. So for example, if the mean function is not continuous, then what you sample that might not be continuous either.
Even if it is continuous, how can we be sure what we sample?
So even if the mean function, so say the mean function is just 0. If this kernel k x y, that would be 0 if x is not y, then it wouldn't be continuous, right? So if all the indexes are independent from each other, it wouldn't be continuous. It just means that in each index, you would sample a Gaussian distribution completely independent from each other. All right, and sometimes in the literature you can even see more ridiculous index sets. So sometimes the index sets could be graphs or strings. So any kind of object between you can define, on which you can define positive semi-definite functions. And in this way you can say, try to do regression on graphs. So the domain each, you want to learn a function that maps a graph to, say, a real number. And what you need is just to define a kernel function k, where x is a graph, y is another graph. Okay, and there are kernel functions on graph, or there are kernel functions on strings. So your fantasy can go wild. What are those crazy objects on which you can define positive semi-definite functions? If you can do that, then you can define a Gaussian process on those objects. All right? Or they could be sets as well. Yes?
We're talking about the confidence that we
Mm-hmm.
get from this, but when we design a kernel, it's not related to the distribution of the data. So how is it related to the confidence? The statistical confidence?
Very good point. So this is where people sometimes get sloppy. So when you define your kernel function k, you implicitly say, what's my confidence? So if you just have a training set, indeed it's not really a confidence. So in statistics, people don't even say it's a confidence interval, they say it's a credibility interval. That's one thing. So it just means that you just estimate your confidence, but that's just the estimated confidence, not the true confidence, right? Second, if you have a validation set, then you might be able to learn a function k as well. You don't need to predefine it. And then it could lead to a confidence interval. But if you just have a training set without validation sets, then you are right that we shouldn't really call it confidence. And I just call it confidence because many people in machine learning call it confidence, although we should know it's not a real confidence, right? That in real problems, why would that distribution, the conditional in regression, why would this always be a Gaussian distribution? So it might happen that, for example, if my data set looks like this, then, so what I want to show that this is x, this is y. On this given x point, the conditional distribution might be multimodal. The Gaussian processes cannot model that. They just model everything with the Gaussian distribution as a conditional distribution. Okay? So I still will say it's confidence interval. Also, it's just an estimated confidence interval, and they might be bad. But in practice, they work well.
Can't you have a mixture of gaussian processes in such a case?
Right, so then things would get crazy. So you could try to do something like that, and in non-parametric Bayesians, people try to study these things, but then the calculations will get complicated. So we will see that with Gaussian distributions, even in our case, the simplest case, the calculations will be quite complicated, but at least for everything there will be a closed formula. If you go to this direction of mixture of Gaussian processes, there will be no closed formula for calculating, say, posteriors. All right, so that was kind of the introduction, and now what we want to do, that if we have a training set of input-output pairs, then how can I fit a Gaussian process that's somehow it's compatible with my input-output pairs? Any questions so far? So this was the simple part. Now comes the complicated. So what we are going to do, that we assume that we have some, so we want to do regression, right? And we assume that we have some prior knowledge on the regression function. Then we get some data, and we want to update our belief on those functions, and we will get a posterior distribution. Okay, so we start with a prior distribution on the regression functions. So as we discussed, the Gaussian process can sample functions from that. So we have a prior Gaussian process. We get some data, input-output pairs, and we update our prior distribution to get the posterior distribution, and that we hope that that Gaussian, the posterior Gaussian distribution will better fit the data. Okay, so for example, in our case, the blue dots are the input-output pairs. And I want to fit a function, learn a regression function from these input-output pairs. And I start with some prior distribution, which was uniform distribution, and that's what I try to illustrate here, that these are the confidence intervals. And what we want is that after I observe these blue dots, I want to update my posterior distribution. So for example, if these were the input-output pairs, then I want the posterior distribution of the Gaussian process to look like something like this. Yes?
Do I really want to have zero variance at the sample?
Very good point. So do I want it or don't I want it? In some cases you want, in some cases you don't. So it's your choice what kind of Gaussian process you want to learn. If you want to allow some variance here too, then you want that in the posterior distribution, these conditional variances shouldn't be zero. If you don't want to allow noise, then you want Gaussian processes such that when you calculate the conditional distributions, then at each input points, the posterior distributions of those Gaussian distributions should be zero. The variance should be zero there.
What are these three colors present?
Oh, these are just present functions sampled from the conditional Gaussian distributions from the sampled from the Gaussian process after I trained the Gaussian process on the data. Okay, so these are the confidence intervals, these gray shapes, and say I sampled regression functions from that Gaussian distributions, they would look like this. So they are all possible regression functions. With Gaussian distributions, I don't want just to say, hey, this is the true regression function. I want a distribution on the regression functions, and I just visualize with some random draws from that regression function.
In the previous slide, it's the same.
And in the previous slide, you can just say that it's the same, that these and these are just some random draws from Gaussian process where, so this is my prior Gaussian process.
Won't you want to show the mean?
So you can, that's another thing you can do, that you can just show the mean like this. That's also a possible visualization. So sometimes people prefer just to show the mean function.
And the variance.
And, or you can add the variance as well. And sometimes people show some random draws from the Gaussian process. Okay, other questions? Okay, so for example, in this case, I show the mean and the variance. We don't have data, then we get some data. And I calculate the posterior distribution, the posterior Gaussian process, and that would look like this, that this is the mean, the blue function, and these are the confidence intervals. And you can see where we have more data points, then that the variance is getting smaller. Where we don't have data points, the variance is still big.
There's no way to represent the covariance on like graphically, right? That's kind of being hidden.
Graphically, how?
Like you're showing the variance at every point?
Yes, but exactly. So I don't know how to do that, because that would be a matrix where each x is a real number and each y is another real.
It sort of encodes like the function should be like you shouldn't like randomly change values. It should be
right. Okay, so the plan for now is to explain that algorithm then can produce this. So you start with some prior knowledge, then you make some observations, training sets, input-output pairs, and then we want to calculate this posterior distribution. Is it clear what we want now? All right.
In the previous graph that you showed, the predicted value is actually outside of, the actual value is outside of the predicted distribution. Does it matter?
So everything, even my prior knowledge, is a Gaussian distribution. Okay, so it means, in case of Gaussian processes, it means that these are just confidence intervals, but things can be outside of that. So say, even if you think that they are, say, the 95% confidence intervals, points can be outside of that, because each marginal is a Gaussian distribution.
So that wasn't in the previous example, it wasn't that way.
So even in the previous...
next one?
Yep.
Yeah, over here, so the data points.
Sure, so you can, right, so that's a good point. So you can either fit such a way that in each data point you can allow error or you cannot allow error. It depends on what you want. Okay, so you can assume that there's some noise in the observations.
That's what you did in the next
yes, but here I didn't. Yes.
So in the previous graph, there was
right. So actually, okay. So these are two different things in that sense. That here I'm showing random draws from the Gaussian process, right? So that's one way of visualizing Gaussian process. In this, I'm not showing random draws from the Gaussian process. I'm showing the mean function of the Gaussian process, and the confidence intervals. But that's true that if I assume that in the input-output pairs I don't have error, then the mean function should also go through those input-output points.
The variance should be 0.
And the variance should be 0 in those points as well. Okay? All right, so this is what we want to do. We want to learn how to calculate these mean functions and these covariance functions. And to do that, we start discuss.
The covariance you're not presenting, you can't see. I mean,
so I want. So in each index, there will be a Gaussian distribution. That Gaussian distribution will have a mean value and will have a covariance or variance. I want to get the formulas of that mean value and that variance. That's our goal. Okay? Other questions? Okay, and to do that, we need to discuss some properties of ridge regression. So now we change topic and we start talking about ridge regression. So this is the notation. We have a training set, D, x, y pairs. We have n pairs. And the linear regression, after some feature map on the input points x, will be defined like this, that it's an inner product between a w weight vector and the feature vector phi of x. And in linear regression, I just want to minimize this cost, this m is n, this cost function. Right? Linear regression, I want to find a w in a vector space that minimizes this cost function. That's a linear regression. In ridge regression, we have this extra term here with some lambda regularization parameter, but we want to minimize this cost function where this m is n. So. All right, so this is the goal of ridge regression. So we will see later, but that will be the bottom line, that a Gaussian process regression is actually just the kernelized version of this ridge regression. So we will see that later. So in other words, the Gaussian process regression, even this, so it's a nonlinear, non-parametric regression. In effect, what it does, that you just do a linear ridge regression in some abstract feature space somewhere. All right, so we will study the properties of this ridge regression.
Wait.
Yep.
So what you said is that ridge regression is just linear regression with.
So it's
where you first like map it up.
Right. So it's linear regression in that sense that there's a linear regression here. It's ridge because there's this penalty term. With Gaussian process, what you do exactly the same thing, but in an abstract feature space. And that's the effect because you do linear regression in a feature space. In your original space, it will be a nonlinear regression. Similarly, like with support vector machine classification, you do.
Oh, you want the thing to be smooth. That's why you're adding the lambda.
Yes. Yep. So with support vector machine classification, it's again just you are doing linear classification, right? But you do that in a feature space, and in effect, it will be a nonlinear classification in your original space. Okay, so notations. These are training set. I create X capital D times N design matrix. So these are just all my input feature vectors, all the N capital D dimensional feature vectors. And Y are the outputs. And our goal is in regression to learn a map that maps Xi to Yi. Okay, and we will just do that with linear ridge regression. Okay, so our regression model is this very simple linear function. F of x is x transpose w. And in this case now, we assume that in each observation, there might be noise. So this is a noisy observation case. So y is just f of x plus some epsilon. If you don't want to allow noise, then this sigma should be 0. And what we do is that we will assume, so we will be Bayesian in this way, which means that we will assume a prior distribution on W weight vectors. We assume that there will be a Gaussian distribution on these W weight vectors. We got the data, and we update our belief in W's. Okay? So this is our model. Again, this is our model. We have some training data. We assume a prior distribution on W, which is a Gaussian distribution. And our goal is that after getting the training data, I want to update my posterior distribution on W's.
So do we include an intercept here as well? So, or do we assume that it is centered at 0? Are we going to have an intercept and non-zero intercept? Are we going to for an intercept as well?
So here, so the means of epsilon, I just assume they are 0.
Right. So y's are going to be centered at 0. That's the assumption.
Oh, the W's, the weights. I just assume that's my prior.
Then I understand. So on the response variable, right?
Y's. So y is just.
So they're expected to have 0 mean? I guess that's what we assume here, right?
That's my prior. I calculate the posterior distributions, and then we will see that the posterior distribution won't be centered around 0. Okay, but I can start with any kind of prior distribution, right, on W. You can change it to anything you want, but I will calculate the posterior distribution. Okay? And it turns out that the posterior distribution of the y's given x, where I marginalized out w's, that won't be centered around 0. So because we only have 5 minutes left, and there will be lots of long calculations, so we continue from here next time. What I would like you to do, to save some time, I would like you to print out the PDF slides, look at it at home carefully, so then hopefully next time we can go through quickly. Because we still have, I think, like 30 minutes to finish these calculations, and then we will start our new topic. All right, so I just finish here for now. And if you have questions, I'm happy to answer it. All right?
What is the next topic after this?
So, right, so we will finish Gaussian processes, and then we will start discussing, the new topic will be latent variable models, and we will discuss independent component analysis and then manifold learning. So probably calculation-wise, I think in this semester the Gaussian processes, they will be the most difficult ones. So if we survive this, then we will be good. Except the learning theory. But oh, homework, please pick them up.
Harry Potter?